AP-270 Moskit anti-ship missile tears through the horizon at Mach 2.5, skimming just meters above the ocean surface. At this extreme velocity, aerodynamic friction heats its titanium nose cone to blistering temperatures, but the real terror is the distance. It is exactly 5 miles away from an Arleigh Burke-class destroyer. For a human operator staring at a radar screen in the Combat Information Center, 5 miles translates to barely 6 seconds until catastrophic impact. Human reflex is officially rendered mathematically useless. Neurological response times simply cannot process the kinetic reality of a multi-ton warhead closing the gap at 850 meters per second. This is the exact microsecond the human element is violently stripped from the equation. The Fleet Defense Protocol is handed over entirely to an autonomous brain. The Phalanx Close-In Weapon System, or CIWS, wakes up from its passive standby state and assumes absolute kinetic control. To understand why naval warfare had to completely eliminate the human trigger finger, we must input the bloody tactical data from the 1982 Falklands War. Let us render the historical scenario on our tactical map. Argentine Super Étendard strike fighters launched Exocet anti-ship missiles against the British Royal Navy. The Exocet utilized a sea-skimming flight profile, flying so dangerously close to the wave crests that traditional shipborne early warning radars were blinded by the chaotic radar returns of the ocean surface, known as sea clutter. The HMS Sheffield was struck, crippled, and eventually sank because the traditional human-in-the-loop anti-air defense network was fundamentally too slow to acquire, track, and engage a low-altitude supersonic threat. Naval engineers realized a fatal flaw in modern fleet defense architecture. You cannot rely on a distributed network of sailors communicating across decks when the enemy missile travels significantly faster than the speed of their voices. The United States Navy demanded a terminal defense system, a last-ditch, stand-alone mechanical predator that required zero external input from the ship's primary combat systems. It needed its own eyes, its own brain, and its own catastrophic teeth, all bolted onto a single, self-contained deck mount. Let us strip away the pristine white exterior of this machine to see how it sees. Execute a material transparency command on the iconic cylindrical white dome sitting atop the gun chassis. Notice that this is not a solid piece of protective metal. It is a specialized composite radome, specifically engineered from advanced fiberglass to be entirely electromagnetically transparent. As we dissolve this outer shell, the true neurological center of the Phalanx is exposed to our viewport. You are looking at a dual-antenna Ku-band radar system. This is not a standard sweeping maritime navigation radar. This is a highly focused, extremely aggressive tracking mechanism operating in the 12 to 18 gigahertz frequency range. Zoom in closely on the upper antenna assembly. This is the search radar. Its sole mechanical purpose is to continuously and relentlessly scan the surrounding three-dimensional airspace, using complex digital signal processing to filter out the chaotic background noise of ocean waves, heavy rain, and flocks of birds. It is looking for one specific physical anomaly, an inbound metallic object moving at high velocity with a rapidly decreasing range. The exact millisecond a target breaks the outer perimeter threshold, the search radar immediately hands the telemetry data down to the second antenna mounted just below it. This lower unit is the track radar. Now, let us pause the 3D simulation and analyze the closed-loop spotting algorithm. This is the software miracle that makes the Phalanx a lethally precise instrument rather than just a blind wall of lead. Most conventional anti-aircraft guns fire a burst. The human operator observes where the glowing tracer rounds go and then manually adjusts the aim to walk the fire onto the target. The Phalanx does not guess, and it does not use tracers. When the system opens fire, the track radar locks its Ku-band beam onto the incoming supersonic missile. Constantly reading the Doppler shift of the radar returns to calculate the exact speed, altitude, and trajectory. But simultaneously, and this is the engineering masterpiece, the exact same track radar is actively tracking the outgoing stream of its own 20mm depleted uranium-ray tungsten armor-piercing rounds. The computer processor compares the spatial coordinates of the incoming threat with the spatial coordinates of its own outgoing bullet swarm in real time. It calculates the three-dimensional angular error between the two intersecting trajectories. It then sends microscopic electrical correction signals to the heavy-duty servo valves controlling the hydraulic drives. Let us visualize the azimuth and elevation drive assemblies located at the base of the turret. These are not simple mechanical gears. We are looking at high-torque hydraulic motors capable of violently snapping a 6,000-pound turret around with pinpoint precision. Imagine the sheer mechanical stress of accelerating that much mass to track a target pulling 10G evasive maneuvers. The system uses a specialized hydraulic fluid, pressurized to thousands of pounds per square inch, pushing through reinforced steel arteries to actuate the movement. If we perform a cross-section cut of the elevation drive axis, you can clearly see the heavy-duty bearings fighting against the extreme gyroscopic forces generated by the rapidly spinning gun barrels. The Phalanx is fighting the laws of inertia every single time it moves. It uses this hydraulic muscle to continuously adjust the elevation and azimuth of the 6 barrels, literally steering the stream of bullets into the nose cone of the missile, closing the geometric gap in a matter of milliseconds. This closed-loop evaluation happens dozens of times every single second. It is a continuous, self-correcting cycle of algorithmic violence. The radar does not just see the enemy. It sees its own kinetic output and forcefully merges the two paths in three-dimensional space. The targeting software is completely ruthless and devoid of hesitation. It classifies targets based on a strict kinematic threat matrix. If a hostile jet is flying parallel to the ship, it is logged in the system but ignored. If a missile alters its vector and turns directly toward the ship's center of mass, the system immediately upgrades it to a priority 1 lethal threat. The Phalanx features a fully automatic engagement mode. In this operational state, there is no human fire authorization button. The exact moment the internal algorithm calculates that the threat geometry intersects with the ship's hull, the system authorizes itself to use maximum kinetic force. The sailors on board the destroyer do not command the weapon. They simply listen to the deafening, mechanical roar of the hydraulic drives spinning up, praying in the dark that the autonomous Ku-band brain computes the firing solution faster than the incoming warhead can detonate. The precise millisecond the algorithm declares a lethal intersection, digital telemetry violently transitions into pure mechanical kinetic energy. We must now strip away the lower gun housing to analyze the executioner. Execute a cross-section Boolean cut on the central chassis to reveal the M61A1 Vulcan 20mm 6-barrel Gatling gun. This is not a conventional gas-operated weapon where the expanding propellant of one fired round cycles the next. That archaic mechanism is fundamentally too slow and prone to catastrophic jamming under extreme thermal stress. The Phalanx utilizes a dedicated pneumatic, or in newer Block 1B variants, a high-torque electrical drive motor mounted directly to the rear axis of the gun block. This external power source forcefully rotates the entire massive 6-barrel cluster, accelerating the heavy chromoly vanadium steel assembly from 0 to 4,500 revolutions per minute in less than half a second. At this extreme RPM, the rotational G-forces threaten to tear the barrels apart from their central retaining clamps. Heat dissipation instantly becomes a critical failure point. If we activate the thermal imaging overlay, you will observe temperatures inside the firing chamber spiking past 1,000 degrees Celsius within a mere 2-second burst. The continuous rotation of the 6 barrels operates as a forced air cooling mechanism, exposing each individual barrel to the ambient ocean air for a fraction of a second before it rotates back into the active firing breech. Observe the linkless ammunition feed system winding its way up from the base structure beneath the deck. Standard disintegrating machine gun ammo belts would instantly snap and jam under the catastrophic shear stress generated by a firing rate of 75 rounds a femtosecond. Instead, we must render the outer casing of the massive ammunition drum completely transparent. Inside, a complex helical auger, operating like a high-speed Archimedes screw, actively pushes the ammunition out of the 1,550-round capacity magazine. The heavy 20mm shells are driven up a hardened steel, Teflon-coated chute, perfectly synchronized with the rotation of the gun barrels, feeding seamlessly into the transfer unit. The transfer unit meticulously strips the live round from the conveyor, seats it deep into the breech, fires it, and violently extracts the spent brass casing in a continuous, uninterrupted mechanical loop. Now, let us isolate a single projectile exiting the muzzle and slow the rendering simulation down to 1/10,000th of a second. The system does not fire traditional high-explosive fragmentation rounds. Chemical explosives are entirely unreliable against the heavy titanium armor, plating, found on the nose cones of modern supersonic sea-skimming threats like the P-270 Moskit. The Phalanx fires armor-piercing discarding sabot rounds, universally known in naval logistics as APDS, specifically utilizing tungsten penetrators. As the round clears the muzzle brake at an extreme velocity of 1,113 meters per second, aerodynamic drag instantly and violently strips away the lightweight plastic sabot casing. What remains in flight is a sub-caliber, hyper-dense tungsten penetrator dart. Tungsten possesses a density almost twice that of standard lead and boasts a staggering melting point exceeding 3,400 degrees Celsius. When this dense kinetic dart strikes the incoming supersonic missile, it absolutely does not rely on a chemical explosion. It relies entirely on brutal, localized physical overpressure and extreme kinetic energy transfer. The tungsten dart punches directly through the missile's aerodynamic cone and rips through the high-explosive warhead payload. The immense kinetic shockwave generated by the impact structurally shreds the complex internal firing mechanisms, severs the electronic guidance circuitry, and physically scatters the volatile explosive compounds into the atmosphere before they can ever achieve a critical detonation sequence. The target is essentially sawed into pieces by a continuous stream of hypervelocity metal. However, we must now pull the camera back and analyze the grim kinetic reality of the combat environment. This brings us directly to the fatal flaw of all close-in weapon systems: a terrifying physical phenomenon known to naval architects and combat engineers as the shotgun effect. The immutable laws of momentum cannot be deleted by a sophisticated Ku-band radar system or a flawless firing algorithm. If a Phalanx successfully shreds a 3-ton anti-ship missile at a dangerously close distance of 100 meters, that massive target does not simply vanish from existence. The conservation of momentum dictates that 3 tons of burning aviation fuel, jagged shredded titanium, and unexploded ordnance continue traveling forward along their original ballistic trajectory at Mach 2. The Phalanx effectively transforms a single, catastrophic guided spear into a massive, uncontrolled shotgun blast of supersonic shrapnel. This sprawling cloud of high-velocity, burning debris will inevitably slam into the unarmored aluminum superstructure of the defending Arleigh Burke-class destroyer. The kinetic impact of this debris cloud obliterates sensitive phased array radar panels, severs critical communication lines, triggers secondary fires on the deck, and causes severe, localized casualties among the crew members caught outside the heavily armored internal citadel. The CIWS is a weapon of absolute last resort, a desperate final kinetic measure deployed only when the outer layers of the fleet defense network have entirely failed. The Phalanx CIWS is undeniably a masterpiece of autonomous mechanical engineering that successfully solves the supersonic threat equation, yet it remains the one terrifying machine every sailor on board prays to never see operate in anger. Thank you for analyzing this kinetic nightmare with DEFUNCT. Make sure to subscribe to the channel, activate the notification bell, and leave your technical analysis in the comments below to secure your place in our next mechanical deep dive.